ventilation, because this is really a big issue in all of the public institutions. And if you look to an old school or a public institution, you have there already a ventilation system. It was constructed in the Russian period, but not maintained and broken usually. Yeah? And only in the last, let's say, 15, 20 years, for those buildings, no ventilation was, no mechanical ventilation was in operation. But in earlier times, there was a ventilation, and for 20 years ago, they knew that ventilation is important. And when it comes now to refurbishments, I think, of course, the first step is that you analyze your demand of fresh air. Yeah? So you should look into your norms, or there are international norms, how much air in cubic meters per hour and person. Usually European standards are between, let's say, 15 and 20 cubic meters per hour per person. And if you have a classroom or a kindergarten with 20 children, so if you consume 20 cubic meters per hour per person and 20 children, you end up with 400 cubic meter per hour. And then the next step is you need to think how to bring in this fresh air into your room. And there you could basically open the door or the windows, which is not very practical. You can use individual systems for each room, but also a centralized system to supply the whole building, which is usually the most expensive way and most probably not in your budget. Yeah? So the most practical solution is to have these individual systems, and if you have a smart designer, he can optimize such systems. For example, you have in kindergarten, you have a playroom, and you have here the sleeping room, and you can use one unit to supply both rooms, yeah? Because usually the children are either in the sleeping room or in the playroom. Yeah? So it makes no sense to install 2 units or units for both rooms, so you can combine it with a small duct system. But therefore also you need a good technical designer who is able to come up with some good ideas. The next issue was baseline. You need to show the results of your projects, the savings basically, and therefore you need to compare, okay, what was before, what was after. And it makes only sense if you compare apples with apples. Yeah? So let's do a concrete example from Georgia. There's a kindergarten, and before the actual consumption was, let's say, 100, but the kindergarten was occupied only 60% because 40% of the rooms were not in a good conditions and they were empty, yeah, so also not heated. So the consumption, the actual consumption is lower than actually the demand of the kindergarten when it's full, yeah. So after the project, you implement some measures and you end up with, of course, maybe 90, yeah. So you have savings of 10, yeah. But after the refurbishment, you have a full refurbished building and it's fully heated and occupied. All rooms are occupied. Yeah? So actually, you cannot compare the situation before and after because the operation is completely different. So this means that you need to calculate the baseline also for the beginning, before the project, with the same conditions as after. And then actually you end up with a calculated baseline with 150, and here then you have savings of 50. Yeah? So this is our approach. We would recommend to have the actual consumption, before the refurbishment, the consumption, the baseline, considering fully heated building, fully occupied, and of course the consumption after the refurbishment. And then you have the option to see the difference, really the actual savings, but also the savings against the baseline. Okay, so these were my comments. Let's start with presentation. The topic is district heating systems, and we have prepared a guideline end of 2018. You see here this the top page. It's about how to refurbish district heating systems, and some recommendations and what we have learned from previous projects. You find this this guideline also in Russian language on our website. You can download it. I would like to start with a little bit of a general approach. I think district heating systems are a very valuable asset of municipalities. But my experience is that municipalities do not really consider this as a value. It's more a headache, exactly. And usually they want to get rid of it. They want to either support the disconnection of consumers because they have less willingness to pay, or social issues as well. So actually it's not very, it's not seen as asset, and it is not seen as a business case. But all European cities are operating district heating systems, and they see it as a business case. Yeah, it's not just a service. They want to earn money. Yeah, and also I would propose that you see this district heating system as a business case and try to expand and improve the system, and not to close it down and disconnect consumers. And maybe, of course, everybody understands big cities have district heating systems, but also small cities and villages can operate successfully district heating systems. And Austria is maybe a good example, because we have a very long history in small district heating systems. We started in the 80s to build district heating systems, small ones, based on biomass, because Austria is very rich in forests. And we have around 1,500 district heating systems, yeah? And they are all over the country. Austria is very small, much smaller than all of your countries. And you see, it's all over the place, yeah? And with an incredible capacity in the meanwhile, yeah? These are 2 coal power plants. So this is really amazing and a big success over the last 30 years. I'm aware that this cannot be copied one-to-one to your countries, but it just shows that also small villages and small cities can operate systems. Yeah? What are the main problems usually? I mean, customers are not satisfied because the service is poor. Usually, low temperatures, high costs, breakdowns, the start of the operation and the end of the operation is just by the calendar and not the real weather conditions. So this creates some dissatisfactions for the consumers, and they try to disconnect and build their own individual system. And this leads to the next problem. We have a decreasing number of consumers and a decreasing heat load, and this means lower revenues for the district heating company, and the operation of the system is not cost effective anymore. This further leads to overdimensioned equipment, huge pipes, pumps and boilers, inefficient operation, and also the cost efficiency is not great then. We have outdated equipment. This leads to breakdowns, high repair costs and unsatisfied consumers. And also a problem is lack of experience in the design and operation of a good modern plant. So, what are the steps in a refurbishment project? I think everybody knows this, but just go quickly through it. First, you should initiate an energy audit, then you do the energy audit, select the refurbishment measures, do the technical design, the authority approval and procurement, here, implementation, and then the monitoring. And I would like to point out the most important steps in this process, and in my experience, the most important steps are during the energy audit and the selection of the refurbishment measures. Here, in this stage, very early stage, you actually determine the main components of the project, yeah? The boiler size, the type of fuel, the location of maybe a new plant, and this determines really all other steps which follow. That's why I think it is very important to spend a lot of, I mean, to think carefully during these steps how to pre-design and how to develop this project. And I would like to point out, pick out some main issues where I think it's important for during the development of such a project. You should analyze your consumer situation. Yeah, you should have available a network plan with information about your consumers. Yeah, which the name or the number of the consumers, the heat load, the pipe system, the dimension of the pipe system, and usually, if I come to a district heating system, they are not able to provide a list of consumers or a network plan within 2 hours or even half a day, because nobody knows their system. And this is really give us really a bad example, because if you do not know your own system, how can you improve or operate it successfully? So I really recommend that there is a good documentation of the existing system. This is, for example, a table of a consumer list. You have here the names of the consumer, the number of the consumer, and link to the network plan. For example, if there's heat substation installed or not, the capacity, heat meter, and for the last year, the consumer data, consumption data. What else you should look at? You should analyze the boiler house operation. What does this mean? You should calculate the efficiency of each boiler, the efficiency of the whole boiler house, the network, the electricity consumption, and the freshwater consumption. And it's also important, I mean, data are in general important for the technical design, because without data, you just guess, yeah? And this is not enough for an efficient system. So that's why you need also electronic heat meters with a data logger, and you should look into this data and find out also about the heat pattern, I mean, the consumption for each hour. And you should read this data and analyze it. And this will give you the consumption pattern for, let's say, for the winter and also for the summer. And this is important for the technical design. This is an example of an example system. Yeah, you have here the boiler house, a biomass boiler, and a gas boiler. You have 4 heat consumers, and here calculations of this operation data. The gas boiler has an efficiency of 90%, very good. 85% for the biomass boiler. The boiler house in total 85.8, and the efficiency of the network, I mean the heat losses in the network, 68%, 86%, yeah. So just as an example. Next step in the process, in the development, you should estimate the future heat demand. Yeah, maybe, I mean, as I mentioned, the district heating system should be seen as business case. You should, or the operator should try to connect additional consumers and to try to sell additional heat so that the revenues will increase, but also the equipment will be used in a very efficient way. And you should think of the realistic potential for future consumers, let's say for the next 1 to 5 years, and then you get the heat load maybe for your district heating system. What else should be considered? Dimensioning of the district heating pipe system. What we see is very over-dimensioned pipe systems. And this leads, of course, to high investment costs. You should use, or the technical designer should use a calculation software for the dimensioning of the pipe system. It's also important that there is a big spread between the temperatures of the flow and the return. So it is recommended to have at least a temperature difference of 20 degrees. We have seen cases with 2 or 3 degrees, which is really not efficient. You spend a lot of electricity in pumping water around without transferring heat. Yeah? So usually the parameters are 90 degrees go out of the system, and let's say 70 degrees should come back. And this means also you have to think about the consumers, and there you have to support also them to come to this 20 degrees. So this means that the designer should also look to bigger consumers and try to optimize their situation as well. Yeah, this is maybe too technical. And here an example of a first dimensioning of pipe system. In this guideline we have prepared a simple table, and with this table you can estimate the pipe diameter for example a new consumer. In this case, as an example case, we have a new consumer of 400 kilowatt. We go into this table here, we see, okay, with a pipe diameter of 65 normative diameter, I can transfer 455 kilowatts with a temperature difference of 20 degrees. So this is sufficient to have this type of pipe. But usually design companies have a tend to over-dimension the pipe diameters because they want to be on the safe side and do not want to risk that there's a problem. Yeah? And so they usually maybe will propose you a bigger diameter, but this will lead to additional investment costs and it's not really needed. What else is important? We are now in the boiler house. You should ask yourself some questions. Yeah? So what is the current and the future heat demand? We discussed this already. What is the heat load and the heat pattern of the heat consumers? And when it comes to biomass systems, is this heat pattern suitable for a biomass boiler? I mean, if you have a heat pattern through the days which go up and down, maybe because of an industrial or a business consumer, then it is very difficult for the biomass system to follow this variation, because biomass boilers are a little bit slow following the heat demand because there's a lot of mass and fuel included. So this needs to be considered. Next question is where to get the fuel from. Yeah? You should really at a very early stage think where are a fuel supplier and how to get the right fuel. Next question is, okay, do I have enough space for the biomass boiler and the fuel storage. A biomass boiler needs more space than a gas boiler, so you need to check first if it's possible to fit a biomass boiler in your maybe existing boiler house. Next question is also, I mean, you need to bring the fuel to the boiler house, and you need also some space to store the fuel, but also, I mean, space for getting the tractor or the truck into this area. The truck needs to turn around. You have to maneuver with a tractor to feed the fuel to the storage. So this needs to be checked as well. Also, when it comes to biomass boilers, there could be some legal requirements which do not apply for gas boilers. For example, emission values. And of course, you should, at a very early stage, also think of a realistic investment cost and operational costs. I would like to show you now a table and explain the difference between a natural gas boiler and a biomass system. There are some significant differences, and each system has some advantages and disadvantages, and the best is to combine the advantages of both systems. So, investment costs, natural gas boilers are usually quite low. Biomass boilers require high investments. The fuel costs, natural gas high, fuel costs of biomass are low. When it comes to the boiler stuff, natural gas boilers do not need really qualified staff, but biomass systems need trained staff and some training. Fuel quality, when it comes to gas, actually this is a standardized fuel, but biomass, the fuel quality is a big issue, and you need to take care of this. Potential to optimize the heat production costs. Yeah? If you have a gas boiler system, I mean, you cannot have an influence on the gas price. You just have to take it, yeah? And you stick to this price. And you have very little room for optimization. Yeah? But for biomass system, you have a lot of room to improve and make the system more efficient and more cost efficient. So this is really a big advantage. Yeah? Just think if you have a big storage, fuel storage, and usually the fuel price during summertime is cheap, but during wintertime is high. So if you have a good storage, you buy a cheap fuel during summertime, store it in your storage, and have it throughout the year. And this is completely different with natural gas. You depend on the international gas market, and you need to buy it for the international price. What else is important? The space requirements. For biomass boilers, you need a little bit more space in the boiler house, and also for the fuel handling and fuel storage. And also a difference is in the operational mode of the boilers. Gas boilers are quite, I mean, you can switch it off and on, and they have actually 0 till 100% range. Biomass boilers, they have a limited range. You cannot decrease the heat load to 0. Usually you operate between 30 and 100%, but the highest efficiency is between, let's say, 70 and 100%. And this is also the reason why you use biomass systems usually for covering the base load with 80, 90, 100% of the load always, and for peak loads, the natural gas boiler system. And yeah, let me show you the most important differences. Investment costs, so biomass boilers are higher than gas boilers. Fuel costs are low for biomass boilers, and the load variation is not so flexible for the biomass boilers. So both systems, natural gas and biomass, has some advantages, and the best is to combine these advantages. And usually you use a combined system. The biomass boilers as a base load, and for the peak loads, the gas boilers. I don't know if you're familiar with this kind of curve, but if you measure each hour the consumption of your system, you get for each hour a value. Yeah? For 1 year, these are 8,760 hours, and if you arrange these values according to their value, you get such a curve. Yeah? And this means you see here the summer operation, and then it starts till the high peak in some days during winter. And this means the highest load, this is 100% is, let's say, 1,000 kilowatt of your highest load, will appear only, let's say, 1 or 2 days during the year. Yeah? You have maybe minus 25 degrees, only 3 or 4 days during the year. And to cover this peak, it doesn't make sense to dimension the boiler for this very high peak, because this is too cost intensive. Yeah? So that's why you dimension and you use the biomass boiler for the base load, let's say 50 to 60%, and the rest will be covered by the gas boiler, because you can easily switch it on and switch it off. And with such a system, you can cover up to, let's say, 80% of the heat demand with the biomass boiler. So the natural gas consumption is quite limited. Another important issue is the control system, because our experience is that also the control system is a little bit neglected, also by the technical design companies. But it is important because you need to combine the biomass boiler and the gas boiler. And actually it's recommended to have an automatic system. And usually the biomass boiler has a more advanced control system, because the biomass boiler has to control a lot of fans and drives. And usually the biomass boiler is, the control system of the biomass boiler is the leading control system, and this system switches on and off the gas boiler. But what is in any case required, a description of the control logic, and this must be included in the technical design and in the tender documents. This is very important, and I very rarely have seen such a description, and if you ask somebody in the district heating company how does the system works, nobody knows. Only the boiler operator knows about his control logic, but there's no information to the boiler staff. Yeah? And what is needed as a minimum, a scheme. You see here three boilers, a biomass boiler, a new gas boiler, and an existing gas boiler, and also a heat accumulator. And what is needed, all the temperature sensors, yeah, here it's added in red. And here it's shown also the overall control system, and the overall control system has to manage all these three boilers, and to switch it on, switch it off, and control actually the load according to the demand of the system. And if you have three boilers, it's already a quite important and difficult control logic, and the technical design company should think of it and write it down. And so this scheme is needed, but also a description as a minimum, okay, when the gas boilers will be switched on, switched off, and also the biomass boiler when it be, for example, switched off. So please make sure that the technical design company is delivering this, and this is should be included in the technical in the tender documents as well. So next issue is the fuel. This is also very important for biomass systems, and As I mentioned, in Austria we have more than 30 years experience in operation of such systems, and the number one problem of such systems is the quality of fuel. If a problem happens in the boiler plant, mainly it's because of the fuel. And therefore you should really take care of this issue. There are some international standards that really describes the quality of fuel, and usually the main characteristics are, I mean, the type of wood, yeah, where does it come from? Let's say we distinguish between two main sources. Virgin woods, I mean directly, let's say from the forests, chemically untreated, yeah? And the second type is chemically treated or coming from some industrial byproducts or residues, yeah? And this chemically treated or some wood waste, it's really tricky, yeah? And it's not recommended for standard boilers. You can use it maybe in a bigger power plant, but in smaller power plants, as we know it, we recommend really just to use virgin wood from the forests. Important is also the particle size, the water content, ash content, the bulk density, and the chemicals included in this fuel. Some criteria. Yeah? The fuel should be available in the region, of course. You do not want to ship fuel from, I don't know, Canada. It should be in the region. You should use international standards. There's a good ISO standard 7225. And the type of fuel and the fuel characteristics must be included in the tender documents. This is very important. And here is an example. You want to purchase a biomass boilers 1000 kilowatt. Type of fuel, you want to use wood chips. Virgin wood type A according to the ISO standard. Water content will be less than 35%. And particle size according to this international standard is so-called P31. And just to give you an impression, this is such type of wood chips. It's, I think, between minimum is 16 millimeters to 31 in average millimeters. And I would like to show you some examples of a problematic fuel. Fuel with a high water content, let's say more than 50%, it's really problematic and should be avoided because the capacity of your boiler plant is really decreasing dramatically. And only in big boiler plants, such wet fuel should be handled. Another problematic fuel is wood chips with larger parts. You see here a mix of large parts, small parts, and usually your fuel supply system gets some problems with these larger parts. They can block the supply line and then stop the boiler. Another problematic fuel is also if you have a high fraction of fine parts. Yeah? Here you see very fine materials mixed, and this can also be a problem for the fuel supply, but also create a lot of dust emissions. And finally, of course, a mix of soil and stones is also not very helpful because it will hurt your fuel supply and also the boiler. You see here a picture, it's just this store the fuel on the just unpaved area. You see here in the mostly mud, and you mix here soil and stones into the fuel, and this should be avoided. So I think I'm at the end of the presentation.